Hello, welcome to this lecture on Introduction to AI in Healthcare. My name's Chris Paton. My background is I'm a medical doctor by training and have been working in research for the last 20 years or so. Most of my research has been in digital technologies in healthcare. I got my MBA from the University of Auckland in 2011 and I have a DPhil in clinical medicine from the University of Oxford. So let's get started. First of all, you might be interested to know where the term artificial intelligence comes from, or AI. So this term came about after a meeting that was held at Dartmouth College in the US in 1956, where some of the leading computer scientists and mathematicians got together to try and figure out how we could use computers to do things that we normally associate with the kind of things that human beings can do. So things like learning or other aspects of human intelligence. And they proposed a 2-month, 10-man study of what they then called artificial intelligence to see whether they could get computers to simulate human intelligence. So it seems quite ambitious now, but many of the people involved, like Claude Shannon, Marvin Minsky, John McCarthy, went on to develop a lot of the foundational concepts of artificial intelligence and using computers for advanced tasks that we associate with human intelligence. So when artificial intelligence first got started, it was generally called symbolic artificial intelligence. And these were also what's called expert systems, nowadays called good old-fashioned AI or GoFi. And basically how this worked would be a computer scientist would sit down with an expert or group of experts and ask them lots of questions and then try and create an algorithm based on the expert knowledge manually in a computer program. So essentially lots of if-then sequences that are based on what humans would do in that situation. Quite often would use structured data sources, and this type of AI is actually really widely used now, although maybe not called AI anymore, just called algorithms. So an example of this is 111 online, where you can use your computer browser or your smartphone to answer questions about your symptoms and find out whether you should go to an emergency department or whether you can kind of manage it at home or whether you need a call back from a nurse. So this 111 uses a system called NHS Pathways, which is this big kind of expert system, kind of decision tree. And even when you call the nurse, they'll use that to kind of navigate where you should go in the NHS. So machine learning, this is probably what we nowadays refer to as artificial intelligence. Machine learning might be a better term for it because the term artificial intelligence is a bit difficult to define. Even the word intelligence is kind of difficult to define. How do you know if something's intelligent or not? But machine learning is kind of a good term because it describes what actually we're trying to do. So really what we're trying to do is create algorithms or create functions, but get the machine or the computer to work out how to create the best function or algorithm. And so there's two kind of main ways of doing this. One is called supervised learning, and that's when you have a lot of data but with the correct answers to what you want to predict. So for example, it might be a lot of chest x-rays that you've got, and you've also got the radiologist's report for each x-ray, and then you want to train a machine learning algorithm to diagnose pneumonia, say. And it can use all of those examples with the radiologist's report to learn what the features are within the image that means it's pneumonia or not. And then eventually, once it's been trained, you can then give it an image without a radiologist report, and it will create a diagnosis for you. So two main types of supervised learning. One is called regression, and this is where you're trying to get the algorithm to give you kind of a number. And you'll probably be familiar, if you've done any statistics in the past, of linear regression, and that's that image up here on the right. I'll just get the laser pointer. This top image, and you can see if you've got some data and you can plot it as a scatter plot, you can normally kind of draw a line through the scatter plot, and you could kind of just do this visually, just put a ruler and just draw a line, what you think is got a kind of even balance of points on either side of the line, and then that line then describes an equation, and the equation is in the form of y equals mx plus c, where m is the gradient of the line and c is the number at the intercept. So this might be like 0.5x plus 7 would give you this line. And what we want to do is we can't, obviously a computer can't look at the points and then use a ruler to draw the line, as you might do in kind of primary school. You need a kind of mathematical way of working out where the line should be. And in normal statistics, if you haven't got too many data points, you can actually kind of solve an equation of reducing the amount of error across the whole group of data points to create a line. But with machine learning, what we normally do is it kind of guesses the line to start with, calculates the overall error, and then adjusts the slope and the intercept, and then calculates the overall error again. And if it's improving, it kind of keeps going in that direction until it stops improving. You can also do supervised classification. So that thing when I was talking about pneumonia or not pneumonia, that's not predicting a number. It's predicting whether something is true or not. And you can also do the same thing, but classifying into one thing or another, and I'll talk a bit more about that in a second. Unsupervised learning, this is where you have just data. You don't have the kind of radiologist reports, you don't have the answers, but you can still get the machine to kind of iteratively go through lots of examples and find patterns. So there might be, if it's lots of points on a graph, it might be clusters of points. Or it might be something within images like, pixels kind of in certain patterns that the machine learning can learn how to recognize. And you can also do what's called generative modeling, where the machine learning algorithm actually just produces new data. And we'll talk a bit about that later. So generative AI is something that we're all familiar with ChatGPT, where it's generating text. Another type of machine learning is reinforcement learning, and that's a bit like the type of machine learning you'd use for robotics or for controlling a spaceship, where the machine learning algorithm creates what's called a policy, so that it can say things like, if the wind's blowing in this direction and the spaceship's leaning on this amount, then it should fire this type of booster. And through lots and lots of examples and simulations, create a policy that works in all kind of environments. So let's dig a bit deeper into these things. This graph on the bottom is this idea of gradient descent. So it's a bit like the graph above, but with an extra dimension. So instead of a curvy line, it's a kind of looks like a landscape, and as in it we use this kind of process of gradient descent for reducing the error when we're plotting the line, and we can do that in 3D as well as in 2D and even in higher dimensions, so you could even end up with thousands of dimensions. But let's just go through regression in a bit more detail. So you can see this animation on the right is the machine learning algorithm learning where to put the line. So it starts off flat, quickly increases the slope, and then just gradually comes to the kind of stop at where it's the best fit. The term regression comes on this idea of regression to mediocrity. And the kind of first use was trying to work out, trying to predict how tall a child would be based on the heights of the parents. This study kind of worked out that if you have a particularly tall parent, it doesn't necessarily mean that the child is going to be as tall, because it was probably an outlier, and you just don't keep getting taller and taller and taller. There's a kind of what's called regression to the mean or regression to mediocrity, where outliers, generally the next point that you measure is going to be closer to the mean than the previous one. So nowadays, that's not really what we're talking about when we're doing linear regression. It's a kind of similar idea, you can imagine, but what it really means is drawing this line of best fit through all of the variables, all of the data points, so that you can then make predictions where you don't have a data point. So it might be something that's further off the line to the right, or it might be something in between data points, and you want to make a good estimate of what the answer would be. And that's also called kind of predicting the results. So it's a model that will predict. Some of the terms we use there are dependent and independent variable. So the dependent variable is what is the kind of prediction that we want, and and the independent variable is what we kind of plug into the prediction. So like the x value, and the y value would be the dependent variable. So as I said, this can be just calculated using the traditional statistical methods, or it can be kind of learned using machine learning and gradient descent. So I'll just have a slide about gradient descent so you can kind of see what we're talking about. So when you plot these regression, a linear regression line, each time you plot it, you can calculate the cost function, which is a point on this graph on the left, which kind of represents how far out you are, how big an error you are, and it's calculated by taking away the data point from its distance from the line, and they're all added up to get the overall cost. And they're actually, each one is squared, because if you didn't square the ones above and below, you'd end up with a cost function of 0. So we square it and then take the square root eventually. But the cost function, so it's a sum of the data point minus the average, and then squared, and then you can plot that. And for simple linear regression like this, it looks like a kind of U-shaped curve, and this is when you change the parameter of your equation, it will take you to a different point on this curve, and what we want to do is get to the lowest point on this curve. So that's essentially what machine learning does, using a process called gradient descent. So it plots a point, finds out what the gradient is at that point, and then moves down in the direction, and you can calculate a gradient of a point on a function or an equation by finding the differential, or the partial differential for each parameter if you've got lots of parameters, and that will give you the gradient, and then you know which direction to go down, and then you take a jump down and then calculate the gradient again, and it's not quite so much, and then again not quite so much, and so you take smaller and smaller jumps until you get to a gradient that's flat, and that will tell you that you've minimized your cost function. So you've plotted a graph that is the best fit for all of the points, and then you can stop there, and that will give you your predictive model or your linear model. And that works not just with one parameter, but if you can add lots of parameters. So this has got 2 parameters, for example, and then you get your graph of your cost function then becomes 3-dimensional. And if you have lots and lots of parameters, your graph becomes multi-dimensional, which obviously you can't plot and see. But you can still do the calculus to find out the gradient for each of the parameters. And so you do the partial differential for each parameter, and you keep going down in the direction until you get to your kind of lowest point or a minima. Obviously you can see on this that you could have gone in a different direction and found another minima. So there is a bit of a problem in machine learning where you might get stuck in what's called a local minima. You might get stuck here when really the best function was down here. And there's techniques for trying to get out of that. But anyway, so essentially we're trying to find the minimum cost function. So I mentioned that you can also use this technique for classification. So instead of doing a linear graph through all of the points, so say you've plotted all of your points and it's pneumonia or not pneumonia. So 0 is no pneumonia, 1 is definitely pneumonia, and then in between is the kind of probability. And so you've got lots of examples of where it's been classified as pneumonia, lots of examples where it's been classified as not pneumonia. And then what you can do is, instead of drawing a straight line, which wouldn't give you a very good classification system, you can do a logistic curve, so a S-shaped curve, and getting the equation for this curve will give you a nice way of deciding whether or not you've got pneumonia or not. Got the probability of house selling versus the price is kind of the classic example used in machine learning courses to talk about this. So so I talked about NHS 111 and how you kind of go through this algorithm. You can also get machines, the computers, to come up with these kind of decision tree algorithms using a kind of similar approach to drawing these kind of true-false or predicting a value. So like this kind of you can use this for regression or classification, and it's kind of just a different way of doing it. And I'm not going to go into the kind of technical details of how decision trees work, but you can have a look at that. But there's lots of different types. You might have heard of random forest. It's quite a kind of common term, and a lot of good, well-used AI systems use decision trees. And there's been a lot of research on how to get computers to learn the probabilities of classification and regression using decision trees. I also mentioned clustering. So this is when you're plotting a graph, you've got all your data points and they seem to be in clusters. And there's some nice machine learning methods of identifying the clusters, and you can do this without any labeling of the data. And so for example, you might have a data set of patients, and you're looking for things like particular diseases, say like hypertension, and you might have clusters of people with hypertension, clusters of people without hypertension. And you're not going to say whether it's diagnosed or not, you're just trying to identify whether there's distinct clusters. And you do this in a similar way, but to linear regression, but you just you put centroids, which are points which initially start off randomly, and then you measure the distance to all of the data points, and then you find where you've minimized the distance to the most data points, and depending on how many clusters that you've got. So you can see that kind of this centroid reduces the minimum to this cluster, and this centroid reduces the minimum to this cluster. So k-means algorithms are quite a common way of doing clustering. So I talked about generative, so we know about generative from things like ChatGPT with generated text, but you can also generate images, text and audio. And the way generative modelling generally works is that you take images and then you apply algorithms to kind of add noise to the image, and then eventually what you can do is start off with noise and ask it to generate images that have got labels associated, that are based on the images that had labels associated with them in the training data. So you can create an image. So you have images that are labelled as cats, and then you add noise to all of the images. And then if you've got a big enough training data set, which you can start with the noise and generate an image with a cat. Lots of different types of generative modelling algorithms now, like VAEs, variational autoencoders, generative adversarial networks, GANs, diffusion models, physics models, lots of different research in generative modelling now. So I mentioned reinforcement learning of this is like landing a rocket ship. So the definition really is the intelligent agent takes actions in a dynamic environment to maximise a reward signal. So you have an agent, and then you kind of look at where the agent is and give it a reward if it's doing the right thing, and it will take actions in an environment and hopefully get rewards. And using that system, you kind of create a policy of what to do in any particular environment. So those machine learning techniques have been around for a long time, and even in healthcare, we're using a lot of those techniques now. So like the NHS 111, the good old-fashioned AI, but also for like radiology images, helping with diagnosis, ECG interpretation, doing risk scores from PPG signals from oxygen sensors, and all of our smartphones and the computers that we use. These types of machine learning techniques have been used for years. Like Gmail uses AI-based spam filters, and it's very kind of common now. So a lot of the more recent excitement has been around deep learning, which is another kind of step forward in artificial intelligence. And this isn't just taking a lot of data and producing kind of a predictive model or a classification system. This is where we use artificial neural networks, which are based on how the brain works. So it's like a network of neurons, and each neuron can either fire or not fire. And then they're all connected together, and for each neuron you kind of add up all of the incoming connections to decide whether it's going to fire, and you eventually end up with an output just like you do with the human brain. It might be like moving your hand or speaking, but with a computer system it's normally producing a number at the end of this network, and that number can represent probabilities or words, or it can just be a number like like house price that we were talking about. So deep learning networks can be supervised or unsupervised, and are commonly used for things like radiology, diagnosis, natural language processing, self-driving cars, and basically allow you to have the simple way of thinking about it is to allow you to have a predictive model with lots and lots of parameters. So it's a way of creating a function or like a mathematical equation where you have lots and lots and lots of parameters, so that it can take lots of different things into account. Now with a deep learning model, you don't necessarily know what the parameters associated with all the nodes in the network, all of the neurons in the network refer to, because the network is trained and it just learns from the data and from the kind of if it was like a radiology diagnosis, it'd be learning from the image that's going in. All of the different pixels might be represented by different input neurons, and then it will take a series of steps to kind of add those up together and multiply them together and come up with a kind of number that might be a probability between pneumonia or not pneumonia. But you don't necessarily know what all of the layers in the network are doing. It might be that it's looking for patterns of pixels that are bright or not. It might be looking for other things, and you don't know exactly what each parameter associated with each node or each weight associated with each node is doing. So all of those different types of kind of machine learning methods, like regression and classification and reinforcement learning, you can do using deep learning methods. It's basically a way of having a much more complex model with lots and lots of parameters, and it's based on the way that the human brain creates models of the world. So an example is, I just turn off my laser pointer. An example is playing computer games. So you take all of the pixels from the screen as the inputs into a neural network, and then the whole network then decides how to use the information from the pixels to control a video game controller. And this game is called Breakout, and basically the reward is the score. So the model knows the score, and the inputs are just the different coloured pixels, and what all the computer can do is move the paddle left or right. And using lots and lots of examples of playing, it can gradually train this neural network to say things like, if all the pixels are looking like this in a particular way, then move the paddle in this direction. And really this network learns to identify where the ball is, and if the ball is in a particular position, where to use the paddle in order to then increase the score. And then the clever thing about this network was it also didn't just take into account the ball, it also took into account the state of the bricks that had been missing. So if bricks were missing on the kind of left-hand side, as you can kind of see it's doing now, it kind of tunnels through and then quickly increases the score as it bounces around along the top. So all of those kind of ideas are then kind of coded by a process of learning into this network of nodes. You can kind of see the example of a network at the top here. So some apps use like this kind of combination of an expert system and machine learning. So one example is a app called Babylon, which allowed you to basically access the GoFi or the expert system of NHS pathways, but using your phone to type in questions as opposed to choosing options. And obviously when you type in a question like, I've got a pain in my stomach, what should I do? You can use more advanced machine learning that's kind of general purpose, called natural language processing, for it to then turn that into what you would have selected from a drop down, and then you can go into this kind of standardized pathway. And so that's like a combination of AI systems. So the advanced AI is not like a medical AI, it's just natural languaging that would work with all sorts of different things, and then uses an expert system that is a medical system. We've been doing some work in Kenya with the Department of Engineering Science at Oxford and the Khemri Wellcome Trust programme in Nairobi. And this project uses a smartphone camera to help diagnose whether children in rural areas of Kenya have gotten severe or non-severe pneumonia. So if they've got severe pneumonia, they need to be admitted to the intensive care unit, and they need to be admitted to hospital and to get IV antibiotics. Whereas if they've got non-severe pneumonia, they might be able to be managed at home and take oral antibiotics. And so this is quite an important decision to make, because going into hospital can be a long travel, might be away from family, and you can also get other infections and things from being in hospital. So it's much better to be treated at home if possible, but then you don't want people to be treated at home and not get the level of treatment that they need So we used some technology that was developed for the NHS, and it was used for monitoring newborn babies. And the idea there was, if you're a premature baby, your skin is quite thin and friable. So if you stick on a heart rate monitor or a breathing movement sensors, and you have to take them off, you can damage the skin. So they developed this system. They used video to see flushing of the skin to measure the heart rate and movement of the chest to do the respiratory rate. And so we're seeing if we can use that same kind of algorithms to differentiate between severe and non-severe pneumonia. So severe pneumonia, you'd have a higher heart rate and breathing rate. You stop breathing very quickly if your lungs are infected. We've also been working in Vietnam and doing a whole range of projects with lots of different universities, looking at how you can use AI technology for replacing what in a high-income country you might do with experts looking at a lot of data and a lot of complicated data. So trying to simplify the decision-making process so that you can have different types of healthcare workers making decisions and helping patients in intensive care units. So the intensive care, they might not be able to afford like extremely expensive monitoring systems, and they might not have as many qualified staff, so they might not have as many doctors or might not have as many ultrasonographers. And so we had a wide range of projects seeing if we could use AI to, instead of having lots of data, just give a risk score so that a nurse can interpret whether a patient is deteriorating or not, and also doing things like helping people with doing an ultrasound scan by using AI to kind of pick up features when they're doing the scan. And my role in that project was to really look at, as these kind of complex AI systems have been developed, how do we actually get them into practice? So we did a lot of work with the nurses and doctors, finding out how they would use the systems, and also looking at the government policies and the plans for putting in electronic systems to make sure that the AI systems developed would be compatible with the type of computers and things that were going to be used. So kind of historically healthcare has been a bit slower than other industries for adopting digital technologies. But you might have noticed this even yourself if you've been to the doctors recently, that there's been quite a wide uptake of the use of AI for what's called scribing. So instead of the doctor typing in the notes when they're seeing you, they use an AI system to listen to the consultation, turn that into a transcript, and then get the transcript turned into the notes. And what's enabled this is ChatGPT, which is a new AI system that I'll talk a bit about how it was developed in a minute, but enables you to generate text and has been pretty successful, and we've all been using it. An AI scribe is basically you'll go to see the doctor or the nurse or the physio or healthcare professional, and they will start a recording when you go into the consultation. It will listen to the entire consultation, get a AI to generate a transcript of that consultation, and then send that transcript to a service like ChatGPT to say, please can you turn this into a medical note that I can copy and paste into the record, obviously with a bit more instruction than that, but that's basically how it works. And so not too complicated technically, but using this very advanced AI system that's developed by ChatGPT and taking advantage of that to make notes. So there was a study in the UK where they asked general practitioners if they were using it, and they found quite a high level of use. For that study, they did ask GPs that were registered with an online portal, so they might have been more technologically interested GPs in the beginning, but definitely the use is by quite a lot of GPs and other healthcare professionals in the UK and in New Zealand, maybe more in New Zealand, I would think. So why is this? Why has everyone started to use this just recently? So we've had transcribing kind of dictation systems for a long time, like Dragon Naturally Speaking, but they've always been quite expensive and kind of just really make a long transcript which you then have to edit. So it doesn't save you a huge amount of time. It only saves you a lot of time if you're really terrible at typing. And so a lot of people now are quite quick typists, so they don't really do much transcribing. However, with ChatGPT, they allowed developers to access the model using their API, which is like ChatGPT model is stored on servers hosted by Microsoft, and then software developers can then kind of rent the use of those models in their applications. So anyone can like create a new app for a smartphone or a browser, and then use this kind of ChatGPT model. And the ChatGPT model, you can tell it to do things like summarize a conversation, and it's pretty good at creating a summary of the consultation. The background to ChatGPT is a company called OpenAI, and you might have heard about that in the news. So set up by Elon Musk and some of the people behind Facebook. And there's other companies as well involved in doing these types of things, called Google and Anthropic and other companies. And really, what they weren't really setting out to do ChatGPT. They were really setting out to do a general purpose AI, so an AI system that can do everything that a human can do, or even be better than humans at general intelligence. So that's what their kind of objective was. And then one of the experiments was ChatGPT, which was to generate text. They did lots of experiments playing computer games and things like that. And because that seemed to be so useful, they've kind of focused on that now. So how does a kind of text generation model work? So they're called large language models. They're called large because they're much bigger models than other types of deep learning neural networks. It means they can create a predictive function. So just think back to that kind of line, that linear regression line. That's what you're trying to do. Predictive function. It's not a straight line with a model like this. It's got maybe billions. So instead of like a straight line, which would have two parameters, one which is the slope of the line and one which is the intercept on the y-axis, this model has got billions of parameters, which is impossible to visualize. But because it's a deep learning model, it's kind of you've enabled it to train this predictive equation that can take billions of things into account to produce an output. And what you do basically is you then end up with an equation. You don't really know what all of the parameters mean, but because it's been trained through lots of examples and it works, we can just use it without even understanding how it works. So how do you create a large language model? So first of all, you get lots of training data. So what you're trying to do with the large language model is produce text. So when you ask a question to ChatGPT, it's basically producing text. And the earlier versions of GPT, like GPT-2, you would just start a sentence and it would complete the sentence. So you would start, an elephant is a large, and then it would say mammal, and getting it to predict that next word is basically what you're training the model to do. So what you do is you get a lot of text, so like Wikipedia or ebooks uploaded to like this ebook pirating website called LibGen, news websites, just generally the internet. So all of the text you can get hold of in the world, and then you just take lots of examples. So you train an artificial intelligence and you give it a bit of a sentence randomly from anywhere in Wikipedia and say, please guess the next word. And to start with, the model will just guess a random word and it won't be right. But then as the model uses this kind of gradient descent process, it can get closer and closer to the correct prediction. And eventually, after training, so you get this enormous model with billions of nodes, billions of parameters. and then because you've got all of the text on the internet, you can feed in every single sentence on the internet, on Wikipedia and ebooks and things like that. And that gives it enough data in order to start getting really good at predicting the next word. And then once it can predict the next word, you can then use that for answering questions. So it knows that an elephant is a mammal, and it knows the answers to other questions. And then the final step is to use reinforcement. So once you've kind of got it as like a chat format, you can then ask humans to have a look at the answers and say whether you kind of rate them and say whether they're good or not, and that kind of improves the whole process of generating text. So there's this idea that a large language model can predict the next word because it knows about the world from having looked at all the training data. So, for example, it can say mammal for an elephant because it knows about what elephants are from all of the different examples with text talking about elephants, and that's what the model has encoded. But there's also an idea that just because you've put all of the data into it and you've got so many parameters, it might just be storing the whole sentence. So when you start writing an elephant is, it just has in the training set that if someone writes that and the word is mammal but it doesn't understand it, and that probably is what's going on. And there's this idea with machine learning of bias and variance. So bias is where you draw the line, or your model is underfitting the data. So you've got data that's clearly a curve, and you've drawn a straight line, that's called underfitting, and that's high bias. And the opposite to that is overfitting, is when your curve is overly complicated, it's trying to go through too many of the data points, and you've kind of overtrained it, you've put too much work into it with the training data, and then when you give it a new data point that's not within the training data, it's not quite right because you wanted a more of an average curve than too like wiggly a curve. So this is these are the two kind of things you balance when you're doing machine learning models. You want to don't underfit but also don't overfit. However, some researchers have kind of shown that maybe overfitting is a good idea if you want something like a ChatGPT application, because actually what people want is the text from Wikipedia in a chat format. And so if it's a massively overfitted model, so you say you've got enough parameters in the large language model to store all of the data in Wikipedia, which is kind of possible. So the model can be several gigabytes big, and Wikipedia might be 2 gigabytes, just the text, because text is stored quite efficiently. And then when you ask it a question, it just basically looks up, it's kind of stored Wikipedia in the model, so it can kind of look up the answer. And you can test this. This is a researcher called Andre Karpathy, who's worked for OpenAI and Tesla and places, showing that if you just start with the text of a Wikipedia article, it actually just produces the whole article, which kind of indicates that it's just stored all the information in the model. So what they kind of were saying originally with things like ChatGPT or large language models is that they were getting the benefits of what's called double descent. So when we talked about bias and variance, so you have underfitting and overfitting, when you start off with a straight line with not very many parameters, you get quite a lot of error. So that's the kind of beginning of this graph here. And then as you add, increase the model size, increase the number of parameters, you start to get really good. And then you get to this point, this is the lowest amount of error. But then you start overfitting. So you've drawn too squiggly a line through the data points where it was, the reality was a smooth curve. And that gets worse and worse as you start adding more and more parameters. Your line gets way too wiggly in the training data, and then when you test it, it doesn't actually work. And that should get worse and worse and worse. But however, once the model gets bigger and bigger, it seems to start turning around, and this is what you see with a lot of machine learning models, and starts getting better again, which is a bit weird. So it's overfitting so much that it's getting better again. And probably what's happening is you've memorized all of the data in the model, and then the model is then starting to use the extra parameters to do what it was doing originally, which is to perform better predictions. So you've memorized all of the data at this point, You've created a massively overfitted model, gone through every single data point, so every data point is stored within the model, but you've still got space in the model as you get bigger, and that extra space basically encodes new things, and can actually use what's been memorised in order to do new, more interesting things than you would do here. And you get to a point where you get down here, as the model gets really big, you're getting back to where you were originally and even improving more than that. So what they were hoping was, so say you take a large language model, starts off random words, starting to get quite useful, can kind of produce words in a grammatically correct way, but it's kind of nonsense, then memorises the entire of Wikipedia, and then starts to kind of understand a bit what Wikipedia is talking about, and then can use that to create grammatically correct sentences that are less and less like nonsense and more like how the human brain works, where we've memorised lots of things but also have got functions for working out what's in our memory and how the world works. So they were hoping that as the model got bigger and bigger and bigger, so like GPT-3, GPT-4, and then GPT-5, they were hoping that it would get even better, but there's kind of a limit. It's just the kind of diminishing returns, and so we haven't really heard much about, like there was a lot of advance between GPT-3 and GPT-4, we haven't really heard much about GPT-5. And it's probably just like marginal gains, and you can imagine the computer power that you need to do bigger and bigger models kind of gets, enormous. And so what you don't want is a chat GPT every time you type a question. You require 1,000 computers to answer it just to get a slightly better answer than previously. So what they're probably doing now is just kind of working in this area where trying to improve computing power and adding extra things onto the model so that it just works around this area where you've got the memorized Wikipedia, you've got some extra clever things for understanding questions, but it's not like super intelligence, which is what they were kind of after with the whole idea. So AI scribes, like I say, so OpenAI, the company who created GPT, lets programmers use the model through Microsoft, and Google also have a similar service, and Anthropic as well is another company does a similar thing. So the AI scribe sends the audio recording of a consultation to the model, which to a not actually to a large language model first of all, to a speech to text model, so a model that takes the audio and turns it into text. Then that text is then sent to a large language model to summarize. So it's the summarization that you couldn't previously do. And so the large language model cleverly summarizes things using those kind of advanced features from the kind of double descent. So technically it's easy to do, but quite hard to do well. However, you've probably heard about this. There are some problems with large language models and this idea that they understand the world, and that's not they haven't been kind of optimized to understand the world. They've been optimized to produce text that these human feedback people thought was plausible and good, but the human feedback people was just kind of outsourced to a company and not paid very much money to look at text. And so the answers are only as good as will kind of pass the test of those people thinking it's good, and also the memorized text on things like Wikipedia and things like that. So you can give it IQ tests, but then the problem is it probably memorized all the answers to IQ tests because that's all on the internet. And similarly in medicine, so like there's been papers saying it can pass the medical licensing exam, but there's examples of questions on the medical licensing exam on Wikipedia, so it might be just this kind of overfitted thing. Also, the text it generates can just be completely made up, so it might not be just regurgitating Wikipedia, it might be just making it random text that kind of passed the bar of being grammatically correct and looking like it was right, and also kind of generates text that seems to be sycophantic, like saying what you wanted it to say. So if you write an essay and put it into ChatGPT, it will never say that's a terrible essay. It will say, wow, that's fantastic, that's a great essay, and you can then ask it to improve it, but it generally is quite sycophantic, and there's been some medical studies saying why that might be dangerous in healthcare. Should AI scribes be regulated for use in healthcare? So these kind of technology happened quite quickly. Everyone started adopting it, but had this been a kind of previous type of AI system, it would have had to have gone through clinical studies before being used. Like, you don't have a radiology diagnostic system for stenting patients that hasn't been, thoroughly tested in research environments. So some people say because it's summarizing the text, if it's summarizing it badly, that's quite dangerous potentially, or if it's adding information into the summary that's wasn't there in the audio, which it can do with this hallucination problem. So there's this idea that if it summarizes, it should be considered like a medical device, like other types of AI systems. And so regulators are trying to work out how to regulate these systems, but they're already quite widely used. One thing to bear in mind really is patients have been listening, as you probably have as well, to all of the worry about the companies like OpenAI and Elon Musk and people like that, and don't necessarily trust the companies. And if you're going to use a system like this, you should have the consent of the patient, should have informed consent. So you should be able to explain to them what I've kind of just been saying about how it works. So the data is sent to, OpenAI servers hosted by Microsoft, and if a patient doesn't like the idea of OpenAI or using their data for training algorithms and things, it's a conversation people need to have. There's a nice article in the Washington Post where one of the reporters goes to see a doctor who's using one of these systems, using kind of a ChatGPT type system to answer patient questions, and it gives an answer where it says they should use steroid cream for their itchy lips after eating a tomato, and that's quite a medical no-no to use steroid cream on your lips, because your lips have got quite thin skin and the steroid cream could be damaging. So the article started off should have been an amazing, this is exciting new technology, to this is a bit of a worry. There's been quite a lot of little studies where kind of enthusiastic doctors have tried to test how good GPT is as a doctor, and one of them was using questions from a forum where doctors would normally answer patient questions, and they copied and pasted the questions into ChatGPT and then got other doctors to decide whether they thought the ChatGPT answers were better than the answers on this forum that were posted by doctors, and they said the answers were better for quality and empathy. But answers doctors post on a public Reddit forum answering patient questions in their spare time is not really the same as a consultation, so you have to take things with a bit of a grain of salt. There's this idea that like we were kind of saying, they wanted to create this kind of super intelligence, so like an AI system that's as good as a human or better, whereas probably what it's doing is using text from the internet and then regurgitating it. So stochastic parrot means taking text from the internet, regurgitating it with a bit of random noise added to it, so it's not exactly the same as the text on the internet. So there's this question or debate about, is it really like a super intelligent thing, or is it just cleverly putting together bits of text? So Google and Microsoft have both had studies where they say they think it's getting like this emergent intelligence. And so if you remember that kind of double descent graph, you can see that you could imagine it could be with enough computing power, but there's kind of diminishing returns, and so you need another kind of step change in computing power really, or some other innovation that allows you to use less computing power in order to get to this kind of super intelligence by the looks of things. So this question of when will we get to artificial general intelligence or artificial superintelligence? So Elon Musk said it would be smarter than the smartest human next year, and he said that in April 9th, 2024. So that was over a year ago. So he wasn't right about that, and he's got a bit of a history about not being right about predictions, which he does admit to, I think, when you see him in interviews. So in 2015, he said there'd be self-driving cars in 2 years. So this person, Geoffrey Hinton, is one of the kind of godfathers of AI, and said in 2016 that radiologists will be obsolete in 5 years. And so this meme is saying 2024, radiologists in regular cars driving to work. So we haven't seen radiologists go out of work yet. and we still don't have kind of mainstream use of self-driving cars. But it doesn't mean to say it's not going to happen. It's just very difficult to predict, and current trajectory is we need new innovation, new technologies to leap forward, which we don't seem to have at the moment. The other side of it is, do we actually want this? Do we want artificial general intelligence, or do we want kind of narrow artificial intelligence good at like helping a doctor put a stent in or helping to check a diagnosis or a drug interaction, but we don't want the AI to take over the whole process of nursing and medicine? So this was an interesting news article from San Francisco where nurses went on strike because of the AI, saying no computer, no AI can replace a human touch. It cannot hold your loved one's hand. It cannot teach a computer how to have empathy. So the idea that people want nursing care, they want doctors to talk to them about their medical conditions. So there's a lot going on. I said there's a lot going on about AI regulation. So the FDA, the MHRA in the UK, World Health Organization, the EU, are all working on regulating and thinking about how artificial intelligence is used in healthcare, and a lot of work going on at the moment. One area of work that I've been doing is around usability modelling. So thinking about how humans can interact with digital technologies, whether that's patients or whether that's clinicians, and making sure that we keep the kind of humans in focus, designed for humans, but using modelling is a technique that we've been investigating, that you can kind of do simulations of how well humans can work with technology through a kind of model of how humans work with technology, and combining that with how the computers work. So we need to ensure AI is safe and effective. So one thing that the regulation's been doing is calling it a medical device, but AI software is quite different from how physical medical devices work, so we need to do some more work there. Most digital health technology doesn't really need this kind of same clinical validation you have with drugs and other kind of high-risk technology. So most of it's just kind of used for admin or in the background. But some things are used for decision-making, and where perhaps even this kind of summarization function needs to be thought about in the same way that we think about drugs, and making sure we do trials and we know whether it works or not, or whether it's making up too much bad information. So these confabulation or hallucination problems means that it makes it difficult to use for clinical decision making. Don't necessarily trust it, can't see where the information's come from. And then finally, just my personal interest really is that even if the AI system works really well in the lab, needs to be thought about how it's going to work in the real world when human beings are interacting with it and using it. There's a long history of digital technology seeming like it's going to be fantastic, and then when the clinicians start using it or when patients start using it, they just abandon it or don't use it because it's too difficult to use or doesn't fit in with their workflows. So thanks very much. Please do email me with any questions, and look forward to hearing from you. Thanks very much.